The next talk is an extensible user interface for Lean 4, and the speaker is Wojciech Nawrocki. Wojciech is a fourth-year PhD student in the philosophy department at CMU. He is interested in interactive theorem proving and computer-assisted mathematics. This paper illustrates an important design space in the development of interactive theorem provers, which is on interactive visual components. Especially as mathematicians begin formalizing more of their work, frameworks that allow users to interact with their proofs visually may become a critical feature in improving the ITP experience to or beyond the level of paper proofs. Without further ado, please take away Wojciech.
Okay, thank you for the introduction. I think the mic's working. Cool. So yeah, I will be talking about an extensible user interface for Lean 4. And this is joint work with Ed Ayers and Gabriel Ebner at Microsoft Research. So I'm interested in computer-assisted mathematics. And so I'm going to try to prove the following theorem by giving the talk from Lean instead. So here's a Lean window. And okay, I need to explain what is happening here. So on the left-hand side, we have Lean source code. And on the right-hand side, we have what's called Lean InfoView. And that's kind of the main vessel for where you get to see information about what you're doing in your Lean development. And so what happens is that when we place our cursor on a command, then we can see some information associated to that command, which I will get into more detail about in a moment, but I just need to align this so that it's visible. Okay, so first slide, what is Lean? Just in case you don't know, Lean is a dependently typed functional programming language, and it's also a proof assistant. Lean was originally developed by Leo Demura at Microsoft Research, and now it's supported by the nonprofit Lean FRO. So Lean 4 is the new version, and unlike Lean 3, it can compile itself, and it's also extraordinarily hackable, which I will get into in a moment. The largest Lean project, as far as I know, is the community-driven library of formalized mathematics called MATLib. MATLib is currently at over 1.5 million lines of proof code, and it seems to be steadily growing. So if you want to do mathematics, there's a good foundation that you can use for that. As I said, Lean is an extensible language. So it's extensible in at least the following sense. We can extend the syntax via a hygienic macro system implemented by Sebastian Ulrich and inspired largely by Racket. And so what we can do with that is, for instance, we can embed domain-specific languages, such as the HTML tags that I use to define the contents of this slide. So here are the HTML. Okay, HTML is not part of Lean by default, but we just defined some extension or some DSL for it. Furthermore, we can define custom commands, such as the #HTML command that instructs the system to display some HTML, such as this slide in the info view. Okay, so when our cursor is anywhere in this command, then we see the slide. And that's what this command does. And in a similar vein, the entire language stack is dynamically modifiable, so you can do all kinds of things that are maybe not there by default. Besides being extensible, Lean provides an interactive environment. So the outputs of Lean commands, right, they're displayed in the info view, which is this panel right here, like I said. And then what we call a widget is a user interface component that extends the info view in some way. So for instance, the HTML display widget that is kind of has a header here, whoops, is an example of a widget. Now, widgets are written in a combination of Lean code and JavaScript code. I know that the functional programming community doesn't love JavaScript, but I think it's actually, in this case, quite important that we support it, because it means that we can use, we can rely on the JavaScript package ecosystem to do all kinds of things. Like, so in this widget, we have like a 3D Rubik's Cube that's drawn using Three.js. And implementing this from scratch would have been a lot of work, but because we can use JavaScript, it's quite simple. Okay, so besides being extensible, we kind of wanted to have another feature in our visual interface for Lean, which is called, which I guess at least I call referentiality. And so I need to explain what that means. Okay, so here's an error message from Rust. Now, I think Rust is known for being one of the better behaved languages when it comes to like documentation and telling users what's gone wrong with the program when something has gone wrong. And the compiler error messages are exemplary in this sense that they kind of tell you quite clearly what's gone wrong and what you could improve. So here's a message that you might see when you write when you try to invoke the frobnify message or frobnify method of the frob trait on some vector of signed integers. And Rust tells you that this trait bound is not satisfied. It tells you, where you've misused this method. And furthermore, at the bottom of the error message, it gives this little bit of help that says that this trait is in fact implemented for a different type, vectors of unsigned integers. Now, this could be helpful because maybe what you meant was to indeed use it on some vector of unsigned rather than signed integers. But if you think about like how this is implemented, what's happening is that the Rust developers, when they were writing the compiler, they kind of guessed once and for all which kind of information might be useful, like in this situation, right? And then they hard-coded that into the compiler. And in this case, they hard-coded a list of, or rather some code that prints a list of other types that implement this trait. But, well, what if we need different information, right? Like what if the compiler developers didn't think of this, or maybe they just didn't bother? So instead, what at least I think is a good idea, and what is the case in Lean is that whenever you see an expression in an error message or a warning or a log message or anything like that, that refers to an expression, to a Lean expression, it really does refer to the underlying data in the sense of having like a pointer to it, right? So if we type 10 plus ABC, so we try to add a number to a string, then we see the following error message, which is that you could not synthesize an instance of hageadd. But if you're new to Lean, you don't know what hageadd is. And so then what you do is just click on it. And you can find out that hageadd is some type class for heterogeneous addition. And similarly, you can find out like what is a string, it's a type of strings and so on. Right. So instead of trying to guess what might be useful, we just give people the capacity to themselves find out whatever it is they might need. And another example of this feature that's a bit more advanced is that we can use it to trace proof automation. So proof automation is useful, tactics are useful, but it can also be sometimes quite confusing, like why some tactic couldn't automatically find a proof, or maybe something else has gone wrong. So in this case, I have an example. Maybe I need to make it slightly larger. Whoops, sorry. I have an example of a proof, which, well, first of all, we have two predicates, P1 and P2. And if the font is too small, please let me know. But I will assume it's OK. We have two predicates, P1 and P2, on some type alpha. We have a function such that if P1 holds of A and P2 holds of A, then we can conclude beta. And beta is indeed what we want to conclude. So we're going to have to apply F at some point. And we have like a value A of which P1 holds, and we have a value A prime of which P1 and P2 hold. Okay, so in this case, you can see that we will have to use A prime because we don't know that P2A holds. And solve by LM is a tactic that can do this automatically. It will try to apply dependent functions that are in the context to the current goal. Okay, and so in this case, it succeeds in solving a proof. But maybe we want to furthermore learn like what it did while it was trying to compute this. And so that's what we can do here. There is a trace which tells you I'm currently working on goal beta. Here's how I did it. And you can expand this search tree and you can find out, okay, first it tried to prove P1A prime. How did it do that? Well, it tried to apply this and this and this, and all of these things failed, but eventually it was able to prove something. And also it tried to go down the search tree for A and failed because there is no proof of P2 of A. right? So, and like all of these things are referential in the sense that you can, click on them and possibly implement other interactions. Okay, so that's the basic idea. And now, like, given this basic idea, I just want to show lots and lots of examples of what we can do with it. So here's a first application. It's in scientific computing. So Tomasz Skrivan is developing this library called Scilene, which is a library for scientific computing. And one thing that it does is it supports kind of mathematically correct symbolic differentiation. That is, you can write programs that talk about actual real numbers as defined in the mathematics library and actual vectors and so on, and verify that your derivatives are correct with respect to some notion of differentiation. And it can also semi-automatically derive a numerical solver given a differential equation. And for that, Tomasz has written some widgets to interactively visualize how physical systems vary over time as given by these numerical solvers. So in this example, well, first there is some Hamiltonian for like a spring sort of system, and then one can derive from that the solver for a wave equation. So there's some derivation of a solver, and given all that, we now have a executable code to solve this system. And what we can do is visualize this on solve it on a periodic domain and then visualize it on the surface of a circle. So here it is. Nothing's happening because the wave is stationary everywhere. But you can click on this widget, and this will add a Gaussian to the system so that it propagates as a wave, and you can kind of do that and use that to like learn something interactively about this physical system. Okay, so that's one example. Next example is in computational mathematics. So there is this, there are various libraries of concrete objects in mathematics that can be useful to find, for example, counterexamples to conjectures, right? So maybe you want to learn whether like every graph of size up to some n has some property, and then you'd learn that it doesn't because here's a concrete counterexample. So that's what the House of Graphs does, is it stores a large database of interesting graphs. And the Lean HOG project by powered by Barcic and Tasak exposes some interesting finite graphs from this House of Graphs in Lean. And they have written a widget that can, in this case, visualize a Hamiltonian path in a graph, right? So a path that touches each vertex exactly once. So another example is in visualizing like computational objects that you have defined. Okay, there are also some applications in theorem proving in aiding the guide of, aiding the process of proving theorems automatically, or not automatically, interactively. Something that it can be is commonly useful in doing so is diagramming what we're doing, right? So what we have written is another widget to visualize proof states using automatic diagramming software, in this case, Penrose. Penrose is great, by the way, you should check it out. And so I have 3 demos of that, one for Venn diagrams, just for sets, and then one for Euclidean geometry that was written by Vlada Szydlaczek based on the formalization by Andrzej Hernandez-Espiet. And also Yuma Mizuno has written a visualization of string diagrams in monoidal categories. So let's show the first demo, the Venn diagrams. Okay, so here's our proof state. We know that S is a subset of U, and T is a subset of U, and R is a subset of S. We want to conclude that R is a subset of U. And so what we can do is click on some collection of these hypotheses, and we see the diagram. If it happens that the diagram is not generic enough, like it might have some specific features that are not actually true on a general model of the situation, you can click here and get a different diagram. And again, it's referential, like these objects refer to the sets, right? Besides learning something about, or like visualizing a proof state, we can also use it to maybe visually construct proofs. So here is an example in Euclidean geometry, the one by Vlada I mentioned. So in this situation, we have 4 points, A, B, C, D. And we want to prove that there exists a line such that A and B are on that line. right? And in Euclidean geometry, this is true. And so so normally, we would go into the proof state on the left side here and write some like let L be some, whoops, be some line. But instead, let's do it in the info view here. So with shift click, we can select some subset of points. Let me just select all of them. And then the widget will show us all the combinations of lines that it is possible to form using those points. And so in this case, I think we want the line BA, right? So we click insert, and that gets added to the proof state. And now we could use this. It gets added here, and now we could use it to finish the proof with BA as the existential witness. And in a similar vein, the string diagrams. So here they are. So string diagrams are something that is useful for visualizing morphisms in a monoidal category. And that is something that mathematicians actually use on paper. So it's good to have it in the proof assistant. Yeah, and Yuma is working on this widget that will show you F tensor G and this whiskering of G and F. And if you move around in the proof state, so maybe like you do the rewrite, then the widget gets updated dynamically while you do that, so that you can see kind of visually how your tactics are affecting the goal. Okay, and so those are some applications in theorem proving. And finally, I wanted to cover briefly some applications maybe in education. So Patrick Massot has this library called verbose lean, which provides an educational domain-specific language that kind of informalizes formal statements into English and French. So I have it here, I think. Yeah. And so this completely redoes lean, or like changes the language to be English in this case, but can also be French instead of symbolic math, or rather in terms of like type theory. And so, well, besides that, what Patrick has produced is some widget where if you select some information in the proof state, then it will suggest to you some list of possible steps that you can take using that information. So in this case, if we select the assumption that f is a continuous function at the point x0, then you can use these suggestions to like proceed with the proof using that fact as your working, well, as the thing that you work off of. Okay. And another application that I have written is a lean port of Tarski's World. I don't know if anyone's, you know Tarski's World. So Tarski's World is this very old, or maybe not that old, but somewhat old visualization of well, let me just show it actually. It's so what you do in Tarski's World is you have a first order theory that allows you to talk about that objects in like a 2D grid that are tetrahedra, cubes, or dodecahedra, and they have various sizes, so they can be medium, small, or large, and they're positioned at various coordinates of the world. And then the point of this is that you can use it to learn first order logic by evaluating various sentences of first order logic on this grid. And so what I've written is a widget to show you how the world looks visually. So here it is. It's a little bit fuzzy, but hopefully you can see it. And what you can do is you can pin it here, which means that even though I move my cursor around, the widget will stay open. And now if I change my world, like if I move this cube a bit forward, then it dynamically updates. And right, so this is like a visual aid to learning how this model of some first order theory works. Okay, so that's Tarski's World. Let me unpin it now. Yeah, and yeah, that's it. Well, okay, let me conclude first, and then I also have some more examples. But so some conclusions. I have to zoom in a bit. So yeah, well, this, we did we brought this library, but really it's a collective effort. There are many people whose work we build on, and some who build on ours. And all of this is only possible thanks to the Lean core development team and the Lean community. We were inspired in this by some pioneering graphical interfaces for programming languages, such as Lisp from the 80s, and NuPerl, the theorem prover, and more recent work in Idris, as well as the rich tradition of theorem proving interfaces. There was a workshop called UITP going until 2018. And just in general, I think rich type systems deserve rich programming environments. It's nice to have those. You can check out the library here. Okay, I guess I should conclude, but I can also show more examples. But thank you for listening. Yeah.
Thanks for the great talk. And let's open the question. Virtual attendees, please leave the questions on the chat. And if you have any questions, please raise your hand.
Thanks for the lovely talk. Thanks for reviving Tarski's world. I'm your only fan in the room apparently, but it's great. I'm trying to understand, as somebody who's also working on visual interfaces for formal methods broadly, what are the principles that, so there's a lot of technology here, and that's fine, that's great. What are the principles that drive, like, how do you decide what is good? When do you make one? How do you evaluate this? I'm interested in sort of the high level questions here.
Right. I think this is kind of a difficult question to answer. So there are lots and lots of academic graphical interfaces which don't really get broad adoption even in academia. I don't know if you should aim for that. It's a question of is the point of academic research to just produce a prototype and end in there, or is it to actually try to get people to use it and make it good?
Sorry, my question was not about adoption, but about evaluation, which is a very different point.
Right. It's related though, no? No? Okay. Okay, sure. Well, as for evaluation, we did not, I can answer that concretely. We did not do a formal evaluation. What we do though is simply ask people who are using it, like the people I mentioned in the talk, what they found useful, and then try to improve that in the next iteration.
There's one question on the chat from Will Crichton. To what extent does this framework make it easy to compose different visual representations? For example, can I combine the widget that unrolls the trace of a rewriting tactics with a widget that visualizes facts as Penrose diagrams?
In short, that specific example, no, because there is a bug, but in general, yes. And when I fix the bug, also that specific example, also yes. If I have a couple of minutes, I can just show more examples. Okay. Right. These are mostly just different visualizations. So we have, so I've written a diagram for a widget for commutative diagrams, which are similar to string diagrams, but different because they apply to any category, right? So here's a visualization of some composition of morphisms. And similarly, when you move around, you can see change. So that can be helpful to understanding algebraic reasoning. I think there was a question in the chat. And then another one is some visual aids for verification of data structures. In a previous talk by Thai, we saw some red-black trees, which I actually have as well. So if you define this balancing function for red-black trees from Okasaki's textbook on functional data structures, and try to prove something about it, it can be useful to see what symbolic tree you're actually proving something about. So you click on that and you see the tree, and there are some symbolic subtrees as well. Okay, maybe I should answer the question.
It's a question from Gregory. Is it feasible for users of the proof assistant to create diagrams in a new domain themselves, or developing widgets sufficiently involved that it looks like more like a community of widget library maintainers?
So the aim is definitely to enable people to build their own visualizations as easily as possible. There are various levels of how easy it is versus how expressive you can be, right? So if you are okay with being, say, limited to just using Penrose and writing something that uses Penrose, then it's relatively easy. If you want to do something more custom and then write your own library, obviously that's more work. But in general, yeah, I mean, I can read the question again just to be sure I understand it. Yeah, no, we aim to make it as easy as possible. So as I mentioned, like these people like Yuma Mizuno, they just kind of do it. I mean, we don't advise them or work with them or anything. They just do it themselves.
Really great talk. Like related to Shirem's question, I had a question about like motivation and evaluation, like for, conducting like this type of research. Like, did you, start from like, using Lean4 as a user and then like got frustrated and then like added the visualization and or how did this project like start in general? And also like, at which point like did you kind of like decide that like this is satisfactory?
Okay. So two questions there. First, motivation. I mean, I think that if you do any kind of, not any kind of, but lots of flavors of mathematics just rely heavily on visual reasoning. Like as humans, we have evolved to be good at that. And so it's kind of a bad situation to get into if you don't have that around. Of course, when you're proving things in a proof assistant, you can still draw things separately on paper, and that is what people do in practice when they're doing like category theory in MATLAB, say. By the way, so category theory, if I remember correctly, was actually my original motivation because commutative diagrams, you really can't do without them. Yeah, but there is no reason to limit yourself to that, so we just made it kind of very extensible. As for how do you decide whether it's enough, I mean, I don't know if it's enough. At this point, where I am with this is kind of trying to leave it there open for people to use and like see what comes out of that, see how they use it, and then maybe learn what could be improved in that process. But it's hard to do in a vacuum.
I guess like you're like, category serious and like, you're like mathematician, like, you're the like user like yourself, right? So I guess like that's a little bit different from like systems people who's like not using the tools that they created by themselves.
Yeah.
So like, when you as a, category serious, like write Lean4 proofs by yourself, like do you find, this tool useful?
Yeah, it can be sometimes surprising where it is actually used. Like, so in fact, in the current, say, MATLAB development, people are using these things for proof construction, such as the verbose Lean widget I showed, where you can click on things and see possible proof steps. So suggestion of just something that suggests proof steps, but in text, nothing like more diagrammatic than that, is being used in practice. I think visualizations are slightly less used. Yeah. Was that, or maybe you had a different question? Okay. Yes. Right.
And it uses every aspect of it's like back and forth, it's going into expressions and input view.
Yeah, but it doesn't show you like a picture. It's just text. Yeah, that's what I meant. So I think, so for commutative diagrams specifically, actually the reason is more technical, while it's not so widely adopted, which is that It only works for goals which are explicitly phrased in the language of category theory. You might have a goal which is actually about categories, but isn't like formulated syntactically as a goal about categories. Like it might be talking about rings or something, and you could translate it into a goal that uses terms from the category theory library, but doesn't. And so there are things like this. But
Thanks again. Let's give him a big applause again.